Hi, this lesson's about polynomial graphs. It builds on some earlier discussion about polynomial functions. First up, the effect of multiplicity on the shape of a polynomial graph. Multiplicities 1, 2, and 3 are most important to know, and they refer to when I have a binomial factor with degree 1, degree 2, or degree 3, as these examples show. You're going to get certain type of graphical behavior when you see these factor patterns with this multiplicity or repetition. So multiplicity 2, degree 2, refers to 2 factors of x minus 1 in this case. The behavior you see graphically are exhibited by these examples here. So in the first case, multiplicity 1, the graph will go straight through the x-intercept, like this parabola, straight through at negative 2, straight through at 1. Or this cubic function, straight through at negative 1, through at 0, and through at 2, represented by these function equations. Multiplicity 2, the graph will bounce off the x-intercept. For example, this parabola at x plus 1 all squared bounces off at the x value of negative 1. Or this reflected parabola with a negative sign in front bounces off at 2, x minus 2 all squared. This can happen on any polynomial like this cubic. It goes through at negative 1, multiplicity 1, but bounces off at positive 1, multiplicity 2. Thirdly, multiplicity 3 relates to graphs that I describe as twisting through the x-intercept. A simple example, y equals x cubed. It does go through, but not straight through. There's a twisting that happens at the x-intercept. This quartic, see degree 1, degree 3, multiplied to make degree 4, goes through at x equals negative 1, multiplicity 1, but twists at x equals 2. So that's shape and multiplicity. Now, next, there's a procedure I suggest you use for graphing polynomials. It involves these 6 steps. First, as we've talked about before, consider the end behavior for large domain values that are positive or negative. So I'm referring to as you move to the far left and the far right. What's happening to f of x? What's happening to the y values? Do they start up high in quadrants 2 or quadrant 2, for example, for negative x, and end up high in quadrant 1, or down in quadrant 3 and end up or down in quadrant 4, perhaps? It all has to do with the degree of the leading term and its coefficient. For example, if I had y equals negative x cubed, I would actually begin I would begin up in quadrant 2 and end down in quadrant 4 because of the reflection. It would look like this. If I had y equals positive x to the 4, I'm going to start up in quadrant 2 and end up in quadrant 1. It's going to look essentially like this for large positive and negative x values. Next, intercepts are important. You find the y-intercept by solving f of 0. You find the x-intercept by factoring if it isn't already factored, and then solving f of x equals 0. Next, find the graph shape at each 0 using multiplicity. We just talked about that up above. Next, find some f of x values at certain domain values in between your known zeros. For example, looking above, if I were trying to sketch this cubic, it would be beneficial to know f of 1, because I know I have an x-intercept at 0 and at 2. I'm not sure how far down this function goes. Substituting 1 into the function would give me that value. Over here, looking at multiplicity 2 case, I've got a 0 at negative 1 and positive 1, but it's helpful to know in between, perhaps at x equals 0 or x equals negative half. Lastly, once you've found all that information, you draw a smooth curve using the information that you know. Polynomials are always smooth, continuous curves. They're not jagged and they don't jump around. That was the bell. Here's an example. Graph this polynomial function. So it's degree 1 here, x is squared here, and x to the 1. So this is x to the 4, effectively. All of these coefficients are positive, so it's a positive x to the 4. I find the y-intercept by setting x to 0. So I would find that the constant term here is 0. And because of the positive x to the 4, it's an even polynomial that will start in quadrant 2 and end up in quadrant 1. The x-intercepts, it's already factored, so I just interpret f of x equals 0. leading to x equals 0, x equals -2, and x equals 1. The -2 is a double x-intercept, or double 0, because of the multiplicity 2. So when I graph it, I'm going to bounce at -2. I'm going to go through at 0, and I'm going to go through at 1. The 0 and the 1 correspond to multiplicity 1. You go directly through. Again, the -2 was squared. I bounce. I start over in quadrant 2. I end in quadrant 1. Some helpful values to know would be f of -1 and perhaps f of 0.5 to figure out how low and how high these points are. Try this next one on your own and then see how you did. Okay, this one has x cubed times another x, so it's x degree 4, or a quartic. This is positive, but this has a negative on the x, so this is a negative leading coefficient. The constant term formed by setting x to 0 would be 2 cubed times 1, or 8. So the y-intercept is 8. This is going to start down in quadrant 3, and it's going to end down as well in quadrant 4. The x-intercepts, it's already factored, are -2, and that's going to be a triple x-intercept, or because of multiplicity 3, and x equals 1, leading to a graph that's going to look like this. -2, 1, start down here, end down here. Let's make a bit of room. And I'm going to twist through here because of the degree 3. I'm going to come back and down through the 1. Now, my y-intercept is 8, but that doesn't mean the peak is at 8. To find that peak, I would probably want to look at y equals, x equals -1, f of -1, and get a sense of where that's at. You try the next one, pause it, and see how you do. Alright, this one, degree 1, 2, 3, and a degree 3 here, so 6, and one more. So this is x to the 7, all leading positive terms. The constant term is -3, 1 squared, -1 cubed, so that's negative, and 2. So -3 times -1 is 3, times 2, 6. So this has a y-intercept of 6. Because it's positive and an odd function, it is going to begin in quadrant 3, and it's going to end in quadrant 1. X-intercepts, it's already factored, so I'm going to have an x-intercept at 3. I'm going to have a -1 double. I'm going to have x equals 1 triple, and I'm going to have -2 single. So 3, -1, 1, -2. Starts down in quadrant 3, ends in quadrant 1. So the -2, I go directly through because multiplicity 1. The -1 is a double, so I'm going to bounce off. I'm going to come up here, I'm going to come down, and at 1, I have a triple, so I've got to twist through there. And then at 3, I've got a single multiplicity, so I come directly through. Again, y-intercept is 6. That doesn't mean the peak is at 6. You'd want to find some values like maybe f of -1.5, f of 2, and so on. All right, next thing we need to do. We need to work all this backwards. So you may be given a graph, or you may be given values of x and y-intercepts, certain coordinates, certain information about multiplicity, and you're going to use that to write the equation. We do the exact process from above in reverse. Here's an example. A polynomial evaluated at 2 gives -16. It has a root of -2 and a double root of 1. I'm going to start by writing a value a that I don't know. It represents the vertical expand or compress and possible reflection. The root of -2 corresponds with saying x plus 2, and there's the starter class. The double root of 1 means x minus 1 gets squared. Now I substitute -16 for the range value. I substitute 2 for the domain value. This leads to a as -4, and therefore p of x equals -4 bracket, x plus 2 bracket, x minus 1 in brackets. And a couple of examples from graphs. Pause, try these out, and see how you do. All right, there's the answer for the first one. I recognized a 0 at negative 2, and it was directly through, so it's multiplicity 1, degree 1. At 1, there's a twist. It's a little hard to see in this, but there's a gentle twist. It doesn't go straight through, so multiplicity 3. I solve for the unknown by substituting values for x and y, leading to negative 2 and my final polynomial. Try the next one. All right, here's the next one solved. Same process. Check through that, and hopefully that all makes good sense to you. By the way, naming these polynomials again for review. This binomial is x degree 1. This is x1 being cubed, so x cubed times x to 1. This is a quartic, degree 4. This one here, I've got 1, 2, 3, 4, 5 degrees, so x to the 5, that's a quintic polynomial. All right, we're almost done. Last thing I'd like to talk about is something called sign diagrams. What sign diagrams do is they summarize signs of f of x, or range values, for certain domain regions that are separated by these zeros or x-intercepts. If I have odd multiplicity, the sign changes on each side of the x-intercept. You go from down to up or up to down. You can look back at previous graphs if that's not clear to you. For even multiplicity, the sign doesn't change because of the bouncing off. So here's a sign diagram. F of x has positive, negative, negative, positive, negative values corresponding to what region it is based on x-intercepts of negative 2, 0, 1, and 3. Now, when I have a sign change here, that tells me that there's an odd multiplicity at x equals negative 2. For example, x plus 2, or maybe x plus 2 cubed, or whatever. When the sign doesn't change, I have an even multiplicity. So that's something like x squared, or x degree 4. Okay, sign change again, so odd, and sign change again, so odd. Now, if I wanted to figure out the minimum degree for this polynomial, the minimum degree caused by this would be 1, caused by this one would be 2, 1, and 1. So I would have 1 plus 2 plus 1 plus 1, or degree 5. This is a quintic polynomial at least. You try the next one, see how you do. Okay, so here I have a sign change representing odd multiplicity, no sign change representing even multiplicity, and again, sign change for odd multiplicity. Examples represented by those x-intercepts are x plus 1, x minus 1 squared, and x minus 2. So the function itself might look like a some unknown value times x plus 1, x minus 1 squared, x minus 2. The graph looks like this. So again, notice how I have positive to negative, and over here I have negative to negative, and then over here I have negative to positive. And it's corresponding with the x-intercepts and giving me a sense of whether or not I'm moving above or below based on multiplicity.